Hopefully you saw my announcement about the confusion this Tuesday. I hope this is a satisfactory explanation of what was going on, but if it's not, please let me know and we can talk about it further. Right, and of course I also sent out a homework assignment. Anybody start yet? Yeah, great. How's it going?
Fine.
Okay, good. No complaints. Not too hard. Not too easy. Okay, good. Right. So then let us continue our discussion of the polar form of vectors. Right. I gave you some picture at the end of Tuesday where I said that this ambiguity of how to define argument results in this pasta-like shape for the complex numbers. And we can see the complex numbers as a twisted plane, right, with many sheets. Okay, so when you look at that picture, hopefully it becomes kind of apparent that actually we can choose any branch cut, a place to cut that spiral plane and get a function for the argument, right? Instead of a multi-valued thing. Okay, so pictorially, I hope you're convinced we can choose any branch cut. Any branch cut. Resulting in a different I don't need quotation marks here, section of our spiral sheet. Right. What I mean is, if we choose, say, tau as the place to cut our infinite spiral sheet, i.e. expressed analytically, I mean the branch which is the half-open interval going from tau to tau plus 2 pi, right? We denote the resulting function by r sub tau of c, right? So just as there are infinitely many sheets on this spiral sheet that we have, we can turn lowercase argument, a infinitely valued thing, into a function in infinitely many ways, just by choosing some real number tau and looking at this half-open interval from tau to tau plus pi over 2. Okay, so in particular, of z is equal to little r with what subscript? Negative pi, yeah, good. Okay, so this is, again, we'll have very little occasion to discuss non-principal values of the argument function. We'll pretty much stick to working with arg, capital arg z, right? But this will actually become quite important to us when we start to discuss integration of functions of a complex variable. Right? It can be useful to us to choose a different branch cut. Okay, so for now, in most of our development, we'll be working with capital arg z, but then eventually we'll see when it becomes useful to take a different branch cut under certain circumstances. Okay. All right. So, why I spent a kind of long time on the development of this concept of argument. That's because it is the gateway to another representation of complex numbers that is extremely useful to us. Okay, so here's the definition. The complex number v equals x plus iy is given in polar form as the following equation: z equals, remember our notation, r just stands for the magnitude of z, plus cosine theta plus I times sine theta, where usually we mean that theta is capital R of z. Of course, R sub tau for any tau makes this equation valid. But as I said before, we'll usually stick with capital R of z, the principal value. Okay? So, let's just do a quick example. What if I ask you to write the complex number 1 plus root 3, or actually, I think it's a little nicer if I put the I in front of the root 3 as opposed to after. I times root 3 in polar form. Okay, so what do I have to do in order to do this? Yeah.
Find the modulus for r and then find theta using the cube.
Yeah. I just have to compute the modulus of this complex number and capital R, or some R, but again we're sticking with capital R mainly. Yeah, good. Okay, so we need the modulus and the argument. So R, the modulus, is just equal to I times 3. This is just the formula from day 1, right? So we have the square root of 1 squared plus root 3 squared, which of course is 1 plus 3. So we get sorted 4 is 2, right? Okay, fair enough. And we have lowercase arc of 1 plus I root 3. Must satisfy. Now, it becomes important that you hopefully saw my last message on Canvas, right? Which I think most of you did, hopefully all of you did. This arc must satisfy cosine of lowercase arc of 1 plus I root 3 is equal to 1 over 2, right? We take the real component of our complex number, 1, and divide it by the modulus, 2. Yeah. And sine of arc of 1 plus I root 3 is equal to root 3 over 2. Now, if you remember trigonometry, we're kind of, this is a nice complex number to work with because, in polar form, because it has some of the standard coordinates for a common value on the unit circle when you memorized that back in trigonometry, right? Okay, so what angle in radians satisfies these two equations? Pi over 3, yeah. So this together implies that arc of 1 plus I root 3 is equal to pi over 3 plus 2k pi for integer k. And in particular, capital arc of 1 plus I times root 3 is just equal to I root 3. Right? I gave you some geometric explanation of why we call capital arc, the choice of branch cut negative pi, our principal value. Here's another way of seeing it algebraically. It's when we let k equal 0, right? So there's no extra copies of 2 pi floating around. It's kind of nicer that way. But again, I can't wait to get to the point where choosing a branch cut will help us integrate certain things. Okay. Good. So, to complete our goal, to write the complex number 1 plus I root 3 in polar form, well, we just write the modulus 2 times cosine of pi over 3 plus I times sine of pi over 3. Okay, so good. Why do we bother changing the format that we write a complex number in? That's kind of a very vague question. Yeah?
Well, for one, it's a lot easier to prove stuff like the argument of the product of two complex numbers is equal to the argument of one plus the argument of the other.
Yeah, right. It has a more natural geometric interpretation. Or maybe not more natural, but it's useful in deducing certain facts. Okay, so let's see what happens when we multiply two complex numbers in polar form and see what we can glean geometrically from them. Okay, so let's let Z1 be equal to R1 times cosine of theta 1 plus I times sine of theta 1. And Z2 be of the same format, a complex number in polar form. R2 times cosine theta 2 plus I sine theta 2. Okay? Then let me just compute explicitly using these formulae, Z1 times Z2. Well, okay, so I can pull the moduli out. Those are just constants, right? So I can put them at front to begin with. Okay, so I'll say this is R1 times R2. And then to multiply the sums, I just do the standard thing I do for multiplying binomials. I FOIL it out, right? So what do I get? As a result of that, I get cosine theta 1 times cosine theta 2. And to get the next summand of the real component, I'll multiply the two terms together that have an I in them. Right? So I get minus sine theta 1 times sine theta 2. Sorry, I missed a delimiter here. I should put a square bracket here and then parentheses so I can clearly separate what's real and imaginary. Okay? So, and then I get plus I times the other two multiplications, right? So I take cosine theta 1 times I sine theta 2, right? So I get cosine theta 1 sine theta 2 plus I sine theta 1 times cosine theta 2, right? So I get cosine theta 2 sine theta 1. Okay, well, this doesn't necessarily look very nice. However, I will somewhat frequently ask you in this part of the course to think back to trigonometry. Do these components remind you of anything? Anybody?
Well, the addition of angle formulas.
Yeah, exactly. This is these are the angle addition formulas for sine and cosine, right? So at first it may seem that we've just expanded the complexity of I shouldn't say complexity, the difficulty of working with an expression for multiplication of complex numbers using the polar form. But once we recognize that each of these are angle addition formulas, it actually becomes quite simple. Okay, so this is in fact equal to R1 times R2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Okay, so what does this tell us is that we want to characterize the complex number z1 times z2 in terms of its polar coordinates. Well, and in fact, in terms of the polar coordinates of z1 and z2 each individually. So what we can say is that the modulus of z1 times z2 is just the product of the moduli of z1 and z2, right? That's the constant term out front here. And the argument of z1 times z2 is just equal to the argument of z1 plus the argument of z2, right? That's the step that we, this is reflective of the step that we deduced at the end using the angle addition formula, right? So this is kind of nice, right? Let's look graphically at what's happening. Okay, so I have some complex number z1, which has a capital argument theta1, and let's say I have some complex number z2, which has capital argument theta2. Well, then in order to multiply these numbers together, I'm trying to make this somewhat accurate. I'll draw the product, z1, z2, which has angle, or argument, capital argument, theta1 plus theta2. Right, so takeaway here is that when you multiply complex numbers together, you can think of it as rotating and scaling. The result is a rotated and scaled complex number. Okay, so, and yeah, I mean, this drawing isn't very accurate, right? I guess z1 times z2 should be much longer, but I think the angles are somewhat accurate. This is just a schematic, right? I hope you get the point from this. Okay, so how about division of complex numbers in polar format? Similarly, for division, we can derive that. I guess I should go to the next board for this. I want my equations to be crammed down the bottom. We can derive that z1 divided by z2 is just equal to r1 divided by r2 times cosine of theta1 minus theta2 plus I times sine of theta1 minus theta2. Okay, so let me give you a little bit of a preview here. What familiar mathematical phenomenon reflects multiplication as addition and division as subtraction? Yeah.
Exponents.
Yeah, exponentiation. This is how exponents behave, right? If you raise something to a sum, you can express that number as a product of the thing you raised to the sum, raised to each summing. That insight will make the polar form of complex numbers extremely useful to you. We'll talk a lot more about that in a short while. Okay, but you can kind of see that now just from these formulae that we are developing. Okay, so let us do an example about computation together. Okay. So let me ask you to firstly write the quotient. 1 plus I divided by root 3 minus I in polar form. Okay, so there's a couple ways to go about this. What do you suggest? What should we do here?
You can convert the top to bottom.
Yeah, I think that's a pretty good way to go. We could convert both of the complex numbers we're taking the quotient of into polar form. And then we just derived how to put that quotient back into the standard polar form, right? Alternatively, you could just use the formula for division that we talked about on the first day, and then convert that single complex number into polar form. And that'll give you the same answer, of course. But I like your suggestion. Let's go with that. Let's convert both of these complex numbers into polar form. Okay? So, convert both into polar form. Okay, so first the numerator, 1 plus I is equal to the modulus of 1 plus I, times, stick with square brackets here, times the cosine of the capital arc of 1 plus I plus I times sine of capital R of 1 plus I. Okay, so what is the modulus of 1 plus I? Root 2, yeah, good. And what is the capital R of 1 plus I? Pi over 4. How did you deduce that?
So it's like the 45-degree angle. It's a 1-1.
Yeah, right, exactly. So that is to say, let's just draw a quick picture. This is 1 plus I, right? So we have side lengths are both equal to 1, and this is a right angle, so this must be pi over 4, right? So this is funny, right? Because, I made this big deal about defining argument, but really, we're just looking at triangles the whole time, right? It's really not as complicated as I made it seem. But it is that complicated when we start to do integration. But that discussion will be worthwhile nonetheless, even though, as I said at the beginning of our discussion about arguments, what we'll do in practice is just take the inverse tangent and decide based on the sign of the components which quadrant we're supposed to be in. Okay? In any case, good. We can pretty easily tell that the capital arc of 1 plus I is pi over 4, right? And there's many ways to do that. Good, thank you. Plus I times sine of pi over 4. Okay. Now let's address the denominator. root 3 minus I is equal to the modulus of root 3 minus I times cosine of arg of root 3 minus I plus I times sine of arg of root 3 minus I. Okay, so what's the modulus of root 3 minus I? Two, yeah, right. We have root 3 squared plus negative 1 squared is 4, and the square root of 4 is 2. Good. Okay, so this is equal to 2 times the cosine of what's the capital arg of root 3 minus 1, minus I, sorry. Negative pi over 6, good. Yeah, so it turns out a fundamental part of complex analysis is remembering the unit circle. So if you haven't looked at that in a while, maybe give it another once over. Or just have a copy of it on hand. You know, looking at it is just as good as remembering it, especially in this day and age. Right, so we got negative pi over 6 plus I times sine of negative pi over 6. Okay. And just to illustrate, I've said this a couple times about, in a practical sense, just using inverse tangent. Let's do that exactly here, right? So, since, and we're lucky here because inverse tangent actually outputs the right value because this happens to be in the range of inverse tangent, right? So the inverse tangent of negative 1 over root 3 is the same as the inverse tangent of negative 1/2 divided by root 3 over 2. Right? Why do I make this bizarre, not the opposite of simplification? Because that's what illustrates that my complex number comes down negative 30 degrees, right? Coordinates of this point are this vector is parallel to the vector with components root 3 over 2 and negative 1/2. Again, going back to the unit circle, right? Okay, good. Okay, so now we have all the information we need to rapidly compute the quotient of these two complex numbers and express it in polar form, right? So all this information together implies that 1 plus I divided by root 3 minus I is equal to the quotient of the moduli. So I get root 2 over 2, right? And for the components, what do I get? I get, again, square brackets are somewhat useful when we have a lot of parentheses flying around. Cosine of pi over 4 minus negative pi over 6 plus I times sine of pi over 4 minus negative pi over 6. Okay, and I do a little bit of arithmetic here. This simplifies to root 2 over 2 of, times cosine of 5 pi over 12, right? 5 pi over 12 plus I times sine of the very same 5 pi over 12. Okay, so fairly routine computations. The only thing that we haven't necessarily practiced a lot together is computing the argument. But like I said, if you go back and look at the unit circle, you'll have a pretty good sense of how to compute the capital arg of many of the examples in the textbook, and often some things I'll ask you. But of course, you can always use a calculator as well to compute the inverse tangent, and then just look at the sign of the components of your complex number to determine what quadrant it is in. And in fact, as promised, that's one of the problems in the first problem set, right? To come up with a valid formula for arc using inverse tangent. Okay, so I hope that's okay. Good. So now let's look at another example that's kind of more geometrically motivating. Okay, what if I were to ask you, secondly, to show that the line through points in the complex plane Z1 and Z2 is normal. Sorry, I should name this line. The line L, let's call it. The line L through 2 points in the complex plane is normal to the line M through points Z3 and Z4 if and only if capital R of Z1 minus Z2 divided by Z3 minus Z4 is equal to plus or minus pi over 2. Okay, so a couple of comments before we start trying to solve this. What does normal mean? Perpendicular. Yep, that's literally Latin. That was the Latin word for perpendicular. Secondly, notice my use of the definite article. That is to say, I say the line L through the points Z1 and Z2. This is a fact from elementary geometry. Any 2 points specifying a unique line. Right? Likewise for M.
So normal means perpendicular in Latin, and ortho means perpendicular in Greek.
Yeah, that's exactly right. Yeah, good observation. In fact, here's a funny thing I noticed earlier this year. I never thought of the similarity, the linguistic similarity, the etymological similarity of orthodox and paradox, right? Somehow orthodoxy is considered normal or perpendicular, and a paradox is something that is wrong, but it's still has an analogy with parallel. I thought that was kind of interesting. That never occurred to me before.
Something that got me was orthodox. You have to make your teeth orthogonal to your gums. I never got that.
Yeah. That's another thing that I never thought of before. That's good.
And I guess the same applies to normal, right? If you're normal, you're in line with everyone else.
Yeah, exactly. Weird how words work like that. Right. So anyway, yeah. Okay. So the value here, what we're saying is that we're always interested to think of ways to determine if lines are parallel to each other or perpendicular. So now we've come up with some formulation of this classic question of how to tell if lines are perpendicular in this case, in terms of the machinery that we've been building over the past week or so. Okay, so that's kind of the value of this. So let's first note that lines L and M are perpendicular. If and only if. Okay, is this okay with everybody? This is somewhat common mathematical notation. I'll just write a little bit less. This just means if and only if. L and M are perpendicular if and only if the vectors, in fact, I should say the vectors or displacements Z1 minus Z2 and Z3 minus Z4 are perpendicular. Okay, so also note the angle between these two vectors is given by capital R of Z1 minus Z2 minus capital R of Z3 minus Z4. Well, by our previous discussion, we can actually go the opposite way here and just compute the arg of the quotient of these two complex numbers, right? So this is equal to the arg of Z1 minus Z2 divided by the arg, divided by the complex number Z3 minus Z4. Okay, so let's pause for a second here. Is this first assertion I made clear to everyone? Right? These 2 points, Z1 and Z2, are on the line L. So the displacement vector between them will be parallel to that line L. Likewise, for the displacement vector between Z3 and Z4, that will be parallel, in fact, lying on the line M. Therefore, this demonstrates our assertion here that L and M are perpendicular if and only if these two vectors are perpendicular, because they each lie on their respective lines or contain their points. Okay, so is this clear? That the angle between these two vectors is given by the difference of their arguments. Well, let's draw a picture of that. Okay, so let's say we have our vector z1 minus z2 here, which has a capital arc of theta 1, and let's say we have our second vector z3 minus z4 here, which has a capital arc of theta 2, right? So if I want to characterize the angle between them, theta, I'll just take theta 1 minus theta 2, right? Okay. So I'm essentially done at this point, right? Hopefully this picture convinces you that this quantity characterizes the angle between our two vectors, which have the same orthogonality properties as our lines L and M. So therefore, they are orthogonal if and only if this quantity, the argument of the quotient, is plus or minus pi over 2, right? Implies exactly what we wanted. L and M normal if and only if the argument of the quotient of the differences equals plus or minus pi over 2. Why the ambiguity with the sign here?
Because it would be like that, or like a 90-degree angle, or like technically a 270-degree angle.
Yeah, exactly. Right? It depends on which
Direction.
which vector, yeah, which direction you're measuring the angle, essentially, between the two vectors. Or in the way I've drawn it here, which vector has the larger argument. Right? You might get a negative pi over 2, but they're still orthogonal. Okay? Good. Keep looking at this clock, but it doesn't work. Okay. So good. So we've introduced this function, which is of great interest to us, capital R. We should see how it interacts with the other things we can do with complex numbers, right? So let's recall z bar, the conjugate of z, is realized as reflection about the real axis. Right, remember that when we take a complex number in the plane, or a point representation, or the vector representation. When we conjugate it, we just flip it over the x-axis. Okay, so what does this tell us about how conjugation interacts with the argument function? Well, what that means is that capital R of the conjugate of z is equal to negative capital R of z. Okay? So, quick picture. Here's z. And here's z bar. Here's my theta, the capital R. And here's negative theta. Of course, this equality depends on the fact that I wrote capital R here. That my choice of branch goes from negative pi to pi. Okay? It's another nice thing about our choice of branch, our choice of principal value, is that we get to say concise things like this. Okay? While simultaneously, consider the argument of the reciprocal of z. Well, by our previous formula for the argument of a quotient, this is equal to the argument of the complex number 1 minus the argument of z. What is the argument of 1? 0. Yeah, it's on the real axis, right? So the angle that it makes with the real axis is 0. Okay, so in other words, the argument of 1 over z is just the argument, the negative of the argument of z. So tell me geometrically what it means that z bar and 1 over z have the same argument. What does that mean geometrically? Any guesses here?
1 over z also reflects over. Is it?
It's not a reflection because the magnitude, the modulus might change, right? In fact, almost always it does, except when your modulus is 1. Yeah.
So is the reciprocal is the rotation clockwise by pi over 2 gradients?
Okay. That's getting closer to what I'm looking for. What I want to say is that what this tells us is that the vectors that z bar and 1 over z represent are parallel. They lie on the same line. Okay, so let's look at a picture. Yeah. So this implies that z bar and 1 over z represent vectors which are parallel. Okay, so in other words, pictorially, let's say we have, here's 1, here's my complex number z, I'm sorry, not z bar, just z. Here's my argument theta, okay? So if I take the complex conjugate, that's not very good, sorry. That's slightly better. So here's z bar, which has argument negative theta. And here's 1 over z. Right? That is to say, since my modulus of z is less than 1, the modulus of 1 over z is going to be greater than 1. Right?
Yeah, just two things.
Yeah.
So 1 over the modulus, 1 over the conjugate of the complex number the argument is just the same as a complex number.
So, yeah, because you'd be negating twice.
And then also, so like if you have 1 over the complex number, and if you multiply top and bottom by the conjugate, you just get a scaling factor at the bottom, and then you get argument below.
Sorry, say that one more time.
So if you multiply by like z star on the top and bottom, you get the conjugate on top. So argument of the conjugate divided by just a scaling factor.
Mhm.
So you can pull scaling factors out of argument. So it's
Yeah.
going to scaling factor times the same thing.
Yeah.
That shows a parallel. But
Well, so you don't pull a scaling factor out of the argument. The argument is just the same for
Yeah.
all the scale factors, right?
Yeah.
So it's not that, that's to say, if you take the argument of a times z,
yeah,
where a is a real number, that's not equal to a times the argument of z.
yeah,
The arguments are the same, right? Okay, just wanted to make sure that was clear. So yeah, that's all correct.
This one.
Okay, cool. Good. So is this okay with everybody? Okay, good. All right. So this is kind of a companion piece to we used argument to show when a couple vectors are perpendicular, and also a condition employing argument to show when 2 vectors are parallel, right? Where a particular pair of vectors are parallel. Okay, so with that, we can move on to discuss the complex exponential. So, if you remember from Calculus 1, when you construct the exponential function, there's a lot of work to be done. Right? You have to first interpret what it even means to raise a number, specifically e, to a real number power, right? It's not totally obvious. Okay, so what I mean to say is integer powers are somewhat intuitive to explain. You're just multiplying that amount of times, right? And then when we discuss taking an exponent that is a real number, there's some work to be done to interpret what that means, to make a sensible definition that agrees with what we want that function to behave like. So similarly, now we want to be able to define the exponential function for a complex input. So we have to do a little work to say what it means to raise e to a complex number. Okay, so let's proceed by doing that now. The complex exponential. Okay, so to do this, what we'll do is we're kind of defining a new thing, a new operation, raising e to a complex number. So in order to do this, we will insist that the operation that we're defining obeys certain properties that the regular exponential for real numbers already obeys. So we want it to at least do certain things. Right? For example, let's insist that for z1 and z2 complex numbers, we have e to the z1 plus z2 is equal to e to the z1 times e to the z2. Okay? This is the familiar property of exponentials of real numbers, right? and I tried to give you a glimpse of this before, that because the angle sum formulae pop out of our development of the polar form of complex numbers, we kind of want to have this property. Yeah, okay? So, in particular, what this means is that e to the complex number x plus yi is equal to e to the x times e to the iy, right? So this, of course, is a complex number, but you can view both x as a complex number with imaginary part 0, and yi as a complex number with real part 0. So we can turn this exponential of a sum into a product of exponentials by our insisting on this. Okay, so here, note that e to the x is just a real number, because we did the work back in Calculus 1 to show this. So, so it suffices to specify what e to the I times y means in our goal of trying to specify what e to a complex number means. Okay? After insisting on this, all we have to do is now define this, a purely e raised to a purely imaginary number. Okay? So what's the other most important property of the exponential function for a real variable? When we first studied e to the x in calculus, what was so great or important about it?
Its derivative.
Yeah, its derivative. The fact that it equals its own derivative. Okay? So we'll also assert that the complex exponential satisfies d e to the z divided by dz is equal to dz, where of course d here is our standard differential notation. Okay. But by what we already made certain, that is to say, we already know that this rule must apply, and that we really just need to consider what it means to compute e to the iy. But by what we've already made certain, this means we want to consider d of e to the iy over dy is equal to I times e to the iy. By the chain rule. Okay? So, where do we go from here? Let's differentiate again and see what happens. Okay? So, this implies that d squared e to the iy over dy squared is equal to d dy of I times e to the iy. Okay? So treat I just like a constant. Yeah? So what we get is that this is equal to negative e to the iy, because I bring another copy of I down, and I times I is negative 1. Okay? So, this means, what does this mean? Well, now I'm really asking you to look back into your mathematical past. Remember when we characterized the exponential function in the context of real variables? We insisted that it satisfied a certain differential equation. Right? That's kind of what we said here. This is what defined the exponential function for real variables. Now, what I'm saying is that this particular complex number, this purely imaginary complex number, when we raise e to that, that function satisfies some new differential equation. So what this means is that the function g of y equal to e to the iy satisfies the differential equation d squared g over dy squared is equal to negative g. Now, anybody take differential equations? Okay, most of us.
Yeah, right now.
You're in it right now, great. So, we know what all solutions to this differential equation look like. Does anybody remember that?
That's a linear combination of sines and cosines.
Yeah, it's just a linear combination of sine and cosine. Okay, so that is to say, all solutions to this differential equation have form. A cosine y plus b sine y for a and b, some complex numbers. Okay? So, check this for yourself. Differentiate this function twice, and you'll see that you get the negative of this function. Now, it takes a little bit more work to show that those are in fact all the solutions, but we won't talk about that here. We're just going to use this fact for differential equations, okay? All right, so this in turn means that our function, our particular function, g of y, e to the iy, we demonstrated explicitly that it's a solution to this differential equation. So what that means, using this fact from differential equations, that all solutions to this differential equation have this form. That means we can write this function, e to the iy, as a times cosine y plus b times sine y. Or some particular A and B. So how do we find A and B?
Boundary conditions.
Let's say that again.
Boundary conditions.
Yeah, boundary conditions or some kind of initial condition. Yeah, exactly. That is to say, there's a particular value that we can plug into this function g and its derivative, its first derivative, that we already know how to compute. What value is that? 0.
Also 0.
Also 0, yeah. 2 pi is a multiple of, or 0 is an integer multiple of 2 pi. But yeah, technically we should pick 0 because we haven't established that y is an argument yet. But yeah, we definitely know how to compute this value when we plug in a 0, right? Because the imaginary part goes away. We just get e to the 0. Okay? To find A and B, use initial values, g of 0 equal to I times 0, which is just 1, right? And g prime of 0, which is equal to I times e to the I times 0, which just gives me I, right? So I'll set g of 0 equal to 1 equal to the generic form of my solution. Okay, what's cosine of 0 is 1, and sine of 0 is 0, right? So I just get A here. So A is 1. Now, if I differentiate my generic solution once, what do I get?
You have negative a sine y plus b cosine y.
Yeah, exactly. The derivative of cosine is negative sine, and the derivative of sine is cosine. So, that is to say, and g prime of 0 equal to I is equal to negative A, sine of 0 plus B cosine of 0, which just gives us B. Okay, so altogether, what this tells us is that e to a purely imaginary number is just equal to cosine y plus I times sine y. Which is called Euler's equation. Okay, so we kind of derive this from a differential equations standpoint, but you can also derive this formula by computing the Taylor series of each side of this and just recognizing that they're equal where they converge. And fact, they converge everywhere. So that's another method that you could. What I mean to say is, you can prove this identity just using calculus too. You don't have to have taken differential equations. But the differential equations approach is kind of nice because we use one of the first examples you see in calculus 1 of a differential equation is used to define the exponential function for real values. Okay? Okay, so let's put this all together. Remember, we're at this stage where we were considering a purely imaginary number because the real component of an exponent, a complex exponent, just separates by our first insistence. But altogether, what we can say now is if C is a complex number in the standard format, then e raised to the z is the complex number with modulus e to the x and polar form cosine y plus I times sine y. Okay, so the first benefit of this derivation is that when we write numbers in polar form, we can now write much less. We can just write z is equal to r times e to the theta, e to the I theta, that is to say. Okay, so this saves us some time in writing polar forms. Right? Because if we have z equal to r times cosine theta plus I sine theta, this is just the same as writing r times e to the I times theta. Or, if you like, expressed again in terms of z. This is the modulus of z times e to the I times the argument of z. Okay. So, just a couple of things to note, which reduces the following identities. Oh, sorry, I made a typo here. This, of course, holds for any of the values that satisfy an argument of z. Right? We could, and sometimes might want to pick an arbitrary argument of z, not necessarily the principal value. Okay, so we get some of the following identities, such as, well, we know what e raised to the I times 0 is, right? Just because that's a real number. But as was already remarked, we can also consider e raised to the I times 2 pi, or e raised to the negative I times 2 pi, or e raised to the I times 4 pi. or e raised to the negative I times 4 pi are all equal to 1, as you were saying. And that's because I let the argument be any value of the argument, any of the values that is an argument for z. Okay, what else do we have that's nice? E raised to the I times pi over 2 gives us what? What's the output of this?
I.
It's just I, yeah. What's the cosine of pi over 2? 0. And what's the cosine, I'm sorry, the sine of pi over 2 is just 1. So we get a 1 here. My modulus is 1, right? There's nothing up front. Okay, so this is just I. Yeah. And of course, everyone's favorite, e times pi to the I is equal to negative 1, right? This is Euler's favorite because e comes from analysis, right? This is like or calculus. Pi comes from geometry. I comes from algebra, right? We introduced that by trying to solve algebraic equations. And negative 1 is, the same thing as what we use to build the integers, right? 1. This is like the identity that spans all important branches of mathematics is what is historically said. It's nice to have a relationship that involves all of them. Right, so even Euler said that was his favorite. Okay, so let's deduce some additional properties of this representation, which I think are not too hard to see. So let's also note that what is the modulus of the complex number e raised to the I times r of z? I kind of just said this already. What's the modulus here?
1.
It's just 1, yeah, because the coefficient on e is 1. Okay? What if we take the product of two complex numbers, both in exponential form? So I get r times e to the I, r sub 1 times e to the I, theta sub 1 times r sub 2 times e to the I, theta sub 2. Well, because I insisted that my usual rules of exponents still apply here, this is just equal to r1 times r2. I pulled the coefficients up front, times e raised to the I times the sum of theta 1 plus theta 2. Okay, so by insisting that my usual rule of exponents still applies, I've recovered what I worked to show about the multiplication of complex numbers adding their arguments. Right? So if I had done this work first, I would have bypassed the use of trigonometric identities, right? I could have just said, oh yeah, the arguments just add when you multiply them by rules of exponents. 6 one, half dozen of the other.
Or you can prove the trig identities with this.
Or that's a very valid point. Thank you for saying that. You could prove the trig identities by using this representation of complex numbers. In fact, maybe today, maybe Tuesday, we'll deduce some less common trig identities in exactly that fashion. So yeah, that's a great observation. Okay, where were we? I got excited and skipped ahead. Okay, similarly, z1 divided by z2 in the exponential form allows us to rederive our formula for a quotient of an argument of quotients and a modulus of quotients. We just get r1 divided by r2 times e to the I times theta 1 minus theta 2. Okay. And furthermore, what can we say about complex conjugation? Oh, sorry. I should start this way. If z is equal to r times e to the I theta, this tells me that the complex conjugate is r times e to the negative I theta. Okay, so these are all just straightforward rephrasings of everything that we did in the first part of class today. Here's something that requires a little bit more recall. Cosine of theta is equal to the real part of the complex number e to the I theta. Okay, remember, we had a formula for the real part of a complex number involving the complex number and its conjugate, right? That is to say, we have this is equal to e to the I theta plus e to the negative I theta divided by 2, right? The real part of the complex number z is equal to z plus z bar divided by 2. And we just said in exponential formulation, z bar is just e to the negative I theta. Okay, cool. We can say similarly for sine of theta equal to the imaginary part of the complex number e to the I theta, which is equal to e to the I theta minus e to the negative I theta divided by 2I. Okay? You might have seen this representation of sine and cosine before and thought to yourself, well, where did the complex numbers come from? Well, really, it's this thing that I erased, Euler's equation. Wait, yeah, Euler's equation. Right? It comes from this correspondence between different ways of representing complex numbers. Okay? So, here's a quick example. Okay, so what if I ask you to compute 1 plus I raised to the 24th power? Well, before today, you might think to just apply the binomial theorem, right? There's a formula for raising a sum of two things together to an arbitrary power. But now that we've come up with the exponential representation of complex numbers, raising a complex number to an arbitrary power becomes much simpler. There's no need to use the binomial theorem. We save ourselves a little computation time because there's no sum in the exponential representation of a complex number. Yes?
So could you compute like cosine of I using those formulas? To get like e to the e to the negative 1 plus e to the 1 over 2.
So say that again. You said you
Like,
wanted to compute cosine of
Cosine
I.
of I.
Cosine of I.
Yeah.
So
Do you use those guys?
So we've remember what the domain of theta is.
Yeah. It is good.
It's not, we would have to do additional work to define what a complex input of a trig function is. We haven't done that. I'm fairly certain there's good literature on this. I can't remember it off the top of my head. I'll send an announcement sometime this weekend about the possibility of doing that. Yeah, but as of the machinery built so far, no, we don't know how to do that. Okay, so let's do something we can do. Let's write our complex number 1 plus I in exponential form, and then see what it is raised to the 24th power. Okay, so what is the modulus of 1 plus I? Root 2, yeah, we computed that earlier. Okay, so this is equal to root 2 times e to the I times, and we also computed the capital R of this complex number. What was it again? Pi root 4, yeah, good. Now I just use the usual rules of exponents. I can distribute the exponent to the factors of a product, right? So I get 2 to the 1/2 power raised to the 24th power times e to the I times pi over 4 raised to the 24th power. So root 2 to the 24 is 2 to the 12th, right? And for my complex exponential, I get e to the I times 6 pi, right? 24 divided by 4 is 6. Now, what is a integer multiple of 2 pi in the exponent of a complex exponential tell us? Then we just get a 1, yeah. So this is just 2 to the 12th. Okay? What do we do here? We took 4 steps to compute this. You would make a lot more computations if you applied the binomial theorem, or even worse, if you just straight up multiply that number by itself 24 times. Okay? So this is extremely useful, this representation. Okay. So I think we'll finish the day by talking about Dumont's theorem, or Dumont's formula, I guess the textbooks call it. Now this is due to Dumont. So let's say for n, a positive integer, we have the following formula, which is really nice. Cosine of theta plus I times sine of theta raised to the nth power is just equal to cosine of n times theta plus I sine of m times theta. In the absence of the exponential formulation of complex numbers, this looks kind of miraculous, right? How does an exponent on a sum of things get into the argument or the input of the functions that make the sum? Kind of weird. But now that we have this beautiful formulation of complex numbers, this makes some kind of sense, right? Let's quickly prove this. Okay, so a couple lines of computation. is the complex number cosine theta plus I sine theta equal to an exponential form? Yeah, it's just e to the I theta. It's to the n. Now, the normal rules of exponents still apply. Okay? E to the I n times theta. Now, we'll go back to standard polar formulation. Okay, so I get cosine of n times theta plus I times sine of n theta. You know, when you write this down, it's like, how did somebody get a theorem named after themselves for this string of computations? Well, it's because he helped develop the whole exponential formulation of complex numbers. He's a contemporary of Euler. They were kind of working at the same time. But, you know, it's kind of insulting for me to write this. And, you know, everything that we did before this was part of the proof. Right? Okay. Don't want to be too disrespectful. Okay, so, yeah, I think we've got 3 minutes left. Let's derive a trig identity using Demoss formula. Let's try to express cosine of 3 times theta in terms of straight up cosine of theta and sine of theta. Okay? So, in order to do this, first note that cosine of 3 times theta is equal to the real part of cosine of 3 theta plus I times sine of 3 theta. Okay? And by De Moivre's theorem, we can pull that exponent out. We can pull this constant out and turn it into an exponent, is what I meant to say. This is the same as the real part of cosine of theta plus I sine theta raised to the n. Okay? So now, then we'll apply, I'm sorry, not the n, raised to the 3. And we're doing the specific number here. Then apply the binomial theorem. Okay, that is to say, what does it tell us in the case of 3? Let me just remind you, this specific case, a plus b to the 3rd is equal to a cubed plus 3a squared times b plus 3a times b squared plus b cubed. So this implies in our case that a cosine of 3 theta is equal to the real part of cosine cubed theta plus 3i cosine squared theta times sine theta plus 3, oh sorry, this is a minus, right? Yeah. Minus 3 cosine theta times sine squared theta minus I times sine cubed theta. Or, in other words, just collecting all the terms which don't have a factor of I get cosine cubed theta minus 3 times cosine theta times sine squared theta. Okay, so if you this always perplexed me when I was in trigonometry in high school. And where do people get trig identities from? Well, here's one answer. Complex analysis. Okay, so have a good weekend. Let me know if there's any questions on the homework, and I'll see you on Tuesday.
What a year already.